discuss about Fourier series representation of a function. So if you have a periodic function with a period 2L, which is a piecewise continuous function in the interval minus LL, then the function can be represented as an infinite series as follows. So the conditions are f of x is a periodic function. A function is said to be periodic with say period 2L if it satisfies the condition that f of x plus 2L is equal to f of x for all values of x. So if a particular function satisfies this particular condition, then it is known as a periodic function. And the second condition is that it's a piecewise continuous function in the interval minus LL. So the interval is of length 2L, and in that interval, the function is a piecewise continuous function. It means the function has only a finite number of discontinuities in the interval minus LL. Then the function can be represented as an infinite series, which is given by f of x is equal to a naught by 2 plus sigma n is equal to 1 to infinity a n cos n pi x by L plus b n sin n pi x by L, where this a n and b n are the Fourier coefficients and a naught are the Fourier coefficients. L is the length of the interval minus L is the interval in which the function is defined, and uh, it has a period or it has a period of length 2L. So here the values of the Fourier coefficients a naught is given by 1 by L into integral minus L to L f of x dx, and a n is given by 1 by L into integral minus L to L f of x into cos n pi x by L dx, and bn is given by 1 by L into integral minus L to L f of x into sin n pi x by L dx. So these formulas are known as Euler's formulas, and this will give the Fourier coefficients. And we get an infinite series representation of the function, and that infinite series representation will converge to the function f of x at the points at which the function is continuous. And remember, we can have a finite number of discontinuous points, and at points of discontinuity the function uh, has a discontinuity, and the infinite series converges to the average of right hand limit and left hand limit of the function at that particular point. For example, if you have a function which has discontinuity at this particular point A, then for all other points the function is continuous. uh, if the function is something like this is a periodic function, and then at a point of continuity, the Fourier series expansion will converge to the value of f of x. And at this particular point in which the function has a discontinuity, the Fourier series converges to the average of right hand limit and left hand limit. So if we approach to a from the left hand side, the value of the function is here, and if we approach to a from the right hand side, for the value of the function is here, and the average is somewhere here. So the Fourier series will converge to this particular point. So at the point of continuity, at all points of continuity, the function will, or the Fourier series will converge to the function itself, and at the points at which the function has a discontinuity, the Fourier series will converge to the average of right hand limit and left hand limit of the function at that particular point. So that's the convergence of Fourier series. And now let us consider a particular example. Consider the function f of x is equal to x. The function f of x is equal to x, inside the interval minus pi less than x less than pi, and it's a periodic function with the period 2 pi, or it is given that f of x is equal to f of x plus 2 pi is equal to f of x for all other values of x outside the interval. Or if you plot the function, it is 0, then from minus pi to plus pi, the value of the function is something like this. F of x is equal to x. Then from pi to pi plus 2 pi, that is 3 pi. This is pi, this is 2 pi, it's 3 pi. Then the value of the function is something like this, and this will continue up to infinity. So we have a discontinuity point here, and here also we have discontinuity point, and this is the function. So in this manner, we can extend the function from minus infinity to plus infinity. That's the nature of periodic function. And now we can have the Fourier series representation of this particular function. So the function is represented as a Fourier series as f of x is equal to a naught by 2 plus summation n varies from 1 to infinity a n cos n pi x by L plus b n sin n pi x by L, and this in this particular case L is equal to pi because it's a periodic function with period 2 pi. So here L is equal to pi, and we can replace all the occurrence of L with pi, and therefore we have the Fourier series representation as a naught by 2 plus summation n varies from 1 to infinity a n cos n x plus b n sin n x. Now just mark it as equation number 1. Now we are going to calculate the values of a naught. A naught is equal to 1 by L. L is equal to pi, so it is 1 by pi integral minus pi to pi, that is minus L to L f of x dx. So here this the formula by which we calculate the Fourier series. So integral minus L to L f of x dx. So into x dx, and that's equal to, either we can integrate using the formula x integral of x is x square by 2 in between minus pi and plus pi, that is pi square by 2 minus pi square, that is pi square by 2 is equal to 0. That's one method. In another simple argument which can be used here is that this x is an odd function, and if we integrate an odd function from minus a to a f of x, if f of x is an odd function, then this integral is equal to 0. So f of x is odd. If f of x is an odd function, then integral from minus a to a f of x dx is equal to here this f of x dx is equal to 0. So we can use that argument directly here, and therefore this integral a naught is equal to 0. So in the same way, a n is given by 1 by pi into integral minus pi to pi f of x into cos n pi x, that is n pi x by L, that is cos n x dx, and that is equal to this. We know that cos of minus x is equal to minus cos x, sorry, plus cos x. Cos of minus x is equal to cos x, and for cosine is cos of x is an even function. In a similar way, cos nx is also an even function, and x is an odd function, and the product of x and cos nx is an odd function. So since cos x into cos nx into x is an odd function, this integrand is an odd function, and therefore this integral from minus pi to pi x into cos nx dx is equal to 0. So this integral is equal to 0, and now the remaining Fourier coefficient is bn. Bn is again 1 by pi into integral minus pi to plus pi x into sine n x dx. So it is sine n pi x by L dx. L is equal to pi, so it is sine n x dx. And we can evaluate this using the integration by parts. So 1 by pi is a constant, just keep it there. Then first function into integral of the second sine nx, the integral is minus cos nx by n, then minus derivative of the first into integral of this particular time, that is minus cos nx derivative is sine n x sine nx by n square, n into n square, in between the limits minus pi and pi, or we can use the rewrite it as 2 by pi into integral 0 to pi x into sine n x dx, because sine minus x is equal to or minus sine nx is equal to minus of sine nx, that is this one is an odd function and x is also an odd function. Product of two odd functions is again product of two odd functions is an even function. So x into sine nx is an even function, and for an even function, if f of x is an even function, then integral minus a to a f of x dx is equal to 2 times integral 0 to a f of x dx. So using this result, we can write it as 2 times integral 0 to pi x into sine n x dx. So that will give a simplification like this, and the limit becomes 0 to pi. This will make things much simple. So this is equal to 2 by pi into so the upper limit and lower limit. Okay, you can just write like this time become positive, so can be written as sine nx by n square minus x into cos nx by n from 0 to pi, and just apply the limits. So sine n pi is 0 upper limit, so 2 pi is a constant, sine pi, sine 2 pi, sine 3 pi, they are all 0, so 0. Then here minus pi into cos n pi by n, then the lower limit sine 0 0, then 0 into cos 0, then plus this is sine 0 by 0, then it is 0 into cos 0 by n, that is again 0. So the remaining term is 2 by pi into uh, minus pi by n into cos n pi. So that's the value of bn. Okay, if you observe the term cos n pi, then as the value of n varies from 1 to infinity, cos pi is um, minus 1. Then cos 2 pi is plus 1, cos 3 pi is minus 1. So it is alternatively minus 1 and plus 1. So this cos n pi can be simply rewritten as minus 1 raised to n. So this expression can be rewritten as 2 by pi into minus pi by pi into, this is minus 1 raised to n divided by n. So this pi and pi will get cancelled, and there is a minus 1 minus into minus 1 raised to n. So can be written as 2 by n into minus 1 raised to n plus 1. So that's the value of the Fourier coefficient Bn. And the other two Fourier coefficients are 0. So what remains is we can express the Fourier series, the function f of x as the Fourier series like this. F of x is equal to a naught by 2, that is 0. Then a naught into cos n pi x by l is again equal to 0. Then plus bn, that is 2 into minus 1 raised to n plus 1 divided by n into sine n pi x by l, or sine x, sine nx, and n varies from 1 to infinity. So that's the Fourier series representation of the function f of x is equal to x, where x varies from minus pi to pi. Then this is equal to, if we rewrite it or if we expand it, what we have is this 2 is a constant, then 2 into as n takes value 1, we have sine x. Then when n is equal to 2, it is minus sine 2x by 2. Then third term is positive, and that term is sine 3x by 3. Then minus sine 4x by 4, then plus etc. This will be the Fourier series representation of the function f of x is equal to x inside the interval minus pi plus pi. So that's a simple example by which we illustrate the process by which we calculate the Fourier series representation of a periodic function. Now, let us illustrate the things using a graphing calculator. So I just plot the function f of x. F of x is equal to x, and anyway, here we plot it from minus infinity to plus infinity, and for the time being, just consider the function only from minus pi to plus pi. So just consider only minus pi to plus pi. Now I just going to add the Fourier series representation of the function here. So it is 2 into sine x minus sine 2x by 2 plus sine 3x by 3 minus sine 4x by 4, etc. So I just going to add the Fourier series representation. So it is f of x is equal to 2 times sine of x. So we get the map of sine 2x, then minus sine of sine 2x by 2, then plus sine of 3x by 3. So far we just consider the first three terms of our Fourier series representation, and the original function f of x, and the function the Fourier series representation becomes so close. If you observe this graphical representation, there is not much difference between the original function and the Fourier series representation. Okay, now we add the fourth term, that is minus sine of 4x by 4, then the fifth term sine of 5x by 5. Okay, now it become very close to the original function. Then if we consider the sixth term also, it is sine of 6x by 6. Okay, as we add more and more terms, as we consider more and more terms in our Fourier series, it becomes very close to the original function f of x is equal to x. So sine 7x by 7. Okay, this is how the Fourier series representation converges to the original function. And observe here, if we consider the points, here is minus 3.14 or minus pi, and this point is plus pi. And at those 2 points, the function is discontinuous, and there the Fourier series converges to some other points. It not converges to the exact value on the function f of x is equal to x. For all other points, if we consider a point here, the function and the sum of the Fourier series are the same. And here also, the function and the sum of the Fourier series converge. And the difference between those two, the series expansion or series representation and the function, are very small. And as we approach to the point of discontinuity, the difference between the original function and the Fourier series representation become large. And at the point of discontinuity, what happens is the Fourier series is not going to converge to the value of the function at that point, or uh, instead of that, the Fourier series representation is going to converge to the average of the right hand limit and left hand limit at that point, and that value is 0. And at the point minus pi and plus pi, these are the 2 points, 3.1415, that's the plus pi. And at those 2 points, the Fourier series is going to converge to the average of right hand limit and left hand limit of the function f of x, or f of x is equal to x in the interval minus pi to plus pi. So that is how the Fourier series representation of a function work. Okay, anyhow we can approximate, or we can use the series representation of the function for approximation purposes, and we just need only to consider just 3 or 4 terms of our Fourier series to have a good enough approximation of the given function. Now let us have another problem. Now consider the function f of x is equal to uh, f of x equal to uh, 2 plus x 2 plus x in the interval minus 2 less than x less than 0, and is equal to 2 minus x in the interval 0 less than x less than 0, and less than 0 less than x less than 2, and it's a periodic function of period minus 2 to 2, and outside the interval is just going to repeat, or in other words it is a periodic function with period 4, and f of x plus 4 or f of x minus 4 is equal to f of x for all values of x. So it's a periodic function with period 4, and if you are going to plot the function, then it is something like let it be minus 2, this is plus 2, from 0 to 2 it is 2 minus x, so when x is equal to 0 it is 2, when x is equal to 2 it is 0, so it is a straight line like this, and in the interval 0 to minus 2 the value is minus 2 plus x, so when x is equal to 0 it is 2, when x is equal to minus 2 it is 0, so this is again a straight line like this. So outside the interval this is going to repeat like this, it is 2 plus 2 4, this is 6, and again here also we have the repetition, it is minus 4, this is minus 6, this, this is 0. So this is the concept of the periodic function, which is represented by f of x is equal to 2 plus x, and is equal to 2 minus x out when 0 less than or equal to x less than or equal to 2, and this is a valve, and we can represent this as a Fourier series expansion, and here L is equal to 2, and therefore the representation of the function is something like f of x is equal to a naught by 2 plus summation n varies from 1 to infinity a n cos n pi x by L plus bn into sin n pi x by L, where a naught is given by 1 by L into integral minus 2 to 2 minus L to plus L f of x dx. But remember, f of x has two different values in two different intervals, so it is equal to 1 by 2 into integral minus 2 to 0 2 plus x dx, and from 0 to 2 2 minus x dx, and this is equal to 1 by 2 into 1 by 2 is common for those two integrals, 1 by 2 into the first integral, it is 2x plus x square by 2 in between minus 2 and 0, and the second integral 2x minus x square by 2 in between 0 and 2, and this is equal to this is equal to 1 by 2 into 0, this will vanish, and at my lower bound minus 2, it is minus 4 plus minus 2 the whole square, that is 4 by 2, then plus here upper bound, it is plus 4 minus 4 by 2, then at 0 this will vanish, and therefore this is equal to 1 by 2 into this minus 4 and plus 4 will get vanish, and so here it is minus of minus 4. Okay, this is our lower bound. So this plus 4. Okay, these two terms will get cancelled and not get cancelled. It is 1 minute. We can take off this like this. Okay. Uh, so what we have is minus of minus 4 is plus 4 plus 4 plus 4, that is 8 plus 8, and here minus 1 by 2, and here also we have a minus 1 by 2, so it is minus uh, not 1 by 2, this is 4 by 2, so it is minus 2 minus 2, that is minus 4, so what we have is 4 by 2, that is equal to 2. So the value of a naught is equal to 2. Now in a similar way we can calculate the value of an. An is equal to integral, okay, 1 by 2 is there, 1 by 2 into integral from minus 2 to 0, it is 2 plus x into cos n pi x by l dx, plus from 0 to 2, this 2 minus x into cos n pi x by l dx. So here also we have to use integration by parts, and that's equal to this 1 by 2 can be taken as a common factor, then it is 2 plus x into integral of cos n pi x by l is equal to sin n pi x by l divided by we are integrating with respect to x, so it is divided by n pi by 2, and it is negative inside, then minus derivative of the first, that is 2 plus x, that is 0 plus 1, so it is 1 into integral of sine is cos n pi x by l divided by nx n pi by 2 the whole square, and here we have a minus sign and that will cancel this minus, so it becomes plus, and the limit is from minus 2 to 0, and in the second integral the integration process is almost the same. This is 2 minus x into minus sine n pi x by 2 divided by n pi x n pi by 2, then minus derivative of the first become minus 1, so it is become plus, then this cos n pi x by 2 by n pi x n pi by 2, and here while taking the integral of sine n pi x by 2, it become minus, of course. So ultimately what happens is the sign become negative. It become negative. This negative. And there are also we have the upper limit and lower limit as 0 and 2. And we cross the square bracket. Now when we apply the limits, it's equal to, here when we apply the limit 0, here we have sine 0 and the limit is equal to 0. Then here when we apply 0, it is cos 0. Cos 0 is 1. So it is 1 by n pi by 2 the square. That's upper limit. Then minus the lower limit, when x is equal to minus 2, the first time will vanish, and when x is equal to minus 2, this particular time become cos of minus 2 into minus, that is cos minus n pi divided by square. Okay, here we don't have a square sign. It is of fast dividend. So that's the lower bound. Then this is our upper bound. This is the lower bound. Okay. Now plus the second integral. The upper bound 2 minus x become equal to 0. So the first time will vanish. Then then here the second time it become minus of cos x is equal to 2, so 2 and 2 get cancelled, cos n pi divided by n pi by 2 the square, then minus the lower bound. The lower bound is again when sine x is equal to 0, the sine 0 will become equal to 0 and that time will vanish. Then here is the minus of minus, that is plus cos 0 is 1 and divided by n pi by 2 the square. Okay, here also we have the square time. And now we just accumulate the terms which are non-zero, which has a non-zero value, and here 1 by n pi square, so it is 1 by 2 into this 2 square is 4 divided by n square pi square, and this term is also 1 by n square pi square by 4, so it is plus 4 times 4 by n square pi square, both are positive terms. Then here cos of minus x is equal to cos x, so it is cos of minus n pi is cos of n pi. So what remains is here it is minus, here also is a negative term, so we can combine these two terms, and we can write it as minus of 2 times cos n pi divided by n square pi square into 2 square. So this 2 square is 4. So this is equal to, we can just cancel 1 by 2 with 2 here, and we add these two times, we get 2. So it is that 4 can be taken as a common factor, and n square and pi square can be taken as a common factor, and what remains is 1 minus this cos and pi can be written as minus 1 raised to n. So we can write it as single time as an is equal to uh, 4 into 1 minus minus 1 raised n uh, divided by n square pi square, and also have a naught is equal to 2. Now we are going to calculate the Fourier coefficient Bn. Bn is equal to, by formula, it is 1 by L 1 by 2 into integral uh, minus 2 to 0 to plus x into 2 plus x into sine n pi x by L dx plus 1 by 2 into this 1 by 2 integral 0 to 2 2 minus x into sine n pi x by L dx. Now, by using the integration by parts, this 1 by 2 is taken as a common factor. This one, these two 1 by 2s are taken outside and keep as a common factor. Then the first function 2 plus x into integral of sin n pi x by L. Sin, the integral is cos minus cos. Sorry, cos n pi x by 2 the all divided by n pi by 2, then minus derivative is 1, and derivative of 2 plus x is 1, and integral of cos is sine n pi x by 2 divided by n pi by 2 the square, and this is integrated in between minus 2 and 0, then plus, okay, here plus the second case it is 2 minus x into integral of sine n pi x by 2, that is minus cos n pi x by 2 divided by n pi by 2. This is minus, then minus derivative of this thing is minus 1, so it becomes positive, then integral of cos n pi x by L, that is sine n pi x by 2 the whole divided by n pi by 2 the whole square, and this minus comes here. Okay, there also this minus will come here, and naturally this become positive, and this integration is between 0 and 2, and therefore this is equal to by applying the upper limit here, can take this 1 by 2 as a common factor, then applying the upper limit and lower limit. Upper limit, this sine 0 by 0, this second time become equal to 0 in the upper limit, and here it is 2 times minus cos 0, this 1 divided by n pi divided by 2, this divided by 2, then minus the lower limit. When the lower limit here 2 minus 2 becomes 0, and the first time will vanish, and here it is x is equal to minus 2. So this minus sine minus n pi divided by n square pi square divided by 2 square, then plus the second integral at upper bound, it is 2 by 2 minus 2 become equal to 0, and the sine term, it is minus of uh, sine n pi divided by n square pi square divided by 4. Then the lower bound, sine 0 becomes 0, and here it is 2 times we have a minus sign, so it becomes plus uh, cos 0. Cos 0 is 1, cos of 0, that is equal to 1. Then what we have is by n pi by 2. We can just rearrange the terms, and what we have is 1 by 2 into minus 4 times by n pi, and a similar term here. So it is uh, yeah, plus 4 times divided by n pi. Then these two terms, this particular term is 4 times sine n pi minus n pi. Sine minus theta is minus sine theta, so it is plus divided by n square pi square. And here it is minus sine n pi divided by n square pi square into this 4 comes here. So ultimately these two terms will get cancelled, and these two will get cancelled, and the answer is 0. So what we have is bn is equal to 0. So the obtained series is a series which contains only the terms of cosines, and the value of f of x is equal to a naught by 2, that is 2 by 2. A naught is equal to 2, so it is 2 by 2 is 1 plus summation from n is equal to 1 to infinity the value of an, which is 4 into 1 minus minus 1 raised to n divided by n square pi square, n square pi square into first one, that is cos n pi x by L. So this will be the Fourier series representation of the function, and this one can be simplified a little by just rewriting the term b an n is equal to 4 into 1 minus minus 1 raised to n by n square pi square. So this is equal to, this become equal to 0 when n takes the values like n is equal to uh, 3, or when varies from 1 to infinity. So when n is equal to 1, uh, it is 1 minus minus 1, that is it becomes plus 2, that is 8 times 8 by n square pi square. When n is equal to 1, n is equal to 3, n is equal to 5, etc. And this is equal to 0 when n is equal to uh, equal to 0 when n is equal to 2, 4, etc. That is here if it is odd and if it is even. For even values of n, this value is equal to 0, and for odd values of n, it is equal to 8 by n square pi square. So this f of x can be rewritten as 1 plus summation from n is equal to 1 to infinity. We just consider this even powered, odd powered terms, and therefore the odd powered terms can be written as uh, for odd powered terms, the numerator is 8, the denominator is n square pi square. That pi square is a constant, so that taken here. Then n square can be written as 2n minus 1 the square. That will represent all the odd power terms into cos uh, n pi x by L can be written as n is equal to 2n minus 1 uh, pi x by L. So this can be written in a simple way as 1 plus 8 by pi square, that's a constant, into summation. Here we use the same index for the summation, so that is n from 1 to infinity. It's not say not uh, to infinity. It is 1 by 2n minus 1 the whole square into cos of 2n minus 1 pi x by 2. So that will be the Fourier series representation of our function f of x. So this particular representation, simplification of an, will make the resulting Fourier series representation much simple, or much looks much uh, elegant. So we can avoid that part if necessary, but that simplification makes the Fourier series representation much simple and much elegant. And this kind of a representation is very useful in further analysis of a Fourier series. So that simplification is strongly recommended. Anyway, let us stop here, and in our next section we will go through more examples of Fourier series and the Fourier series representation of even and odd functions, and a lot more related concepts. So for the time being, let's stop here, and we will meet with uh, problems about Fourier series. So, Thank you.